week and do some extra stuff. Probably starting on Monday, but then the week after that, not next week, but the fifth week, remember, is your first exam and the redo opportunity. We'll have more information and full details on that posted to Piazza next week. We are on Piazza and we are on YouTube live stream, so if you have any questions, you can post there. Otherwise, just raise your hand. We do have our other screen back now. Yay! All right. So we went through for loops, right? That you use the keyword for. We went through while loops, and we went through the nuances and differences between the two. But then we also did an exercise that demonstrated when you might want to use one or the other. In this particular case, when you don't know up front how many iterations you're going to go through the loop, that's probably more appropriate, or more natural at least, to use a while loop, right? We counted up the number of digits in a number here, okay? There are some other issues dealing with loops, including nested loops. Just like you can have an if-else-if statement, an if statement within an if statement, you can have a loop inside a loop, right? We refer to them as the outer loop and the inner loop. So let me go ahead and go back over to VS Code here, and let's go ahead and just write these two loops. Now, an idiomatic for loop, I'll go ahead and create a variable here called n, and I'll set it equal to 10. The idiomatic for loop here would be for int I equals 0, I is less than n, I plus plus. And if I print out I on each iteration, remember it goes up by 1, it starts out at 0 and goes up to 9. I is equal to %d and the line. And if I were to compile this, it's going to have the exact same behavior as before. I don't know if we started at 0 or 1, I forget. But here we're starting at 0, right? 0 up to 9. Now, if instead of just putting a print statement inside that loop, if I did another loop, right? In fact, I'm going to be lazy about it, and I'm going to cut and paste and put it right there. Right? Is there a problem with that, potentially? How many i's do you see now? How many variables named I do you see? 2, right? Is that going to work? I don't know. Let's find out what happens. The compiler is perfectly happy with it. Right? So which I is that actually printing? Right? I don't know. Right? So C is going to let you do this, but should you do this? Probably not. So we've been using I as a placeholder here. I is actually short for iterator variable or increment variable or index when we eventually get to arrays. And that's why we've been using I. Well, what can we use next? J. That's it, J, J. And there's where you get yourself into an issue if you copy and paste, copy and paste. What if I change 2 of them, but I forgot 1 of them, right? I am going to change both of them. There we go, all 3 of them. And let's print them both out. J is equal to %d, and we'll print out both I and j. Now we're doing a loop inside of a loop. So think about what that's going to do. When I is 0, it's going to execute that inner loop how many times? 0 up to 9, so 10 times, right? When I is 1, it's going to execute 10 times. When it's 2, 10 times, right? So how many times total is this going to actually execute? 100. Let's see if we're right. Count. I'll start my counter at 0, because if I don't, what value does count have? Who knows? Maybe 0, probably 0, but it could be dead beef. In addition to printing, I'm going to go ahead and say count plus plus. Add 1 to the counter. And then after the entire program is done here, I'm going to print out what the value of count is. Okay? Let's see if we were correct. 100. We were correct. Why? Well, for each value of I, 0 through 10, it's going to print on j, 0 through 9. There's I is 1. Then j is going to be 0 through 9. There's I is 2. And then 0 through 9. 0 through 9 until we get to 9 at the bottom. All right? Let's kick that up a notch. What if it's 100? How many? What's my count going to be? How many times am I going to be printing something? 100 times on the inner for loop, 100 times in the outer for loop. We call that 10,000. 100 times 100. Okay. Let's find out. All right, in a blink of an eye still. A little bit slower, a little bit noticeably slower. Right? Let's kick that up one more notch. 1,000 thousands. We call them millions. All right. There's a million. I wonder how quick it's going to be now. We're not even through 100 yet. Right? So programs are I/O bound, input-output bound, meaning that the vast majority of the program time here is stuck here just printing stuff out to the screen. Let's go ahead and get rid of that and make it faster. Now we're doing a million things. Right? We're doing it instantaneously again. Right? It was I/O bound. So let's go ahead and continue kicking it up a notch. An order of magnitude greater, 10,000. 10,000 times 10,000 is going to be what? 100 million? Now, is that going to be representable by an integer count? Yeah, because remember it's a maximum of 2.147 billion. 100 million can fit. Oh, did you see it? It's kind of delayed there. All right. Let's kick it up one more notch. Now it's 100,000 times 100,000. How big is that? What do we call that? No? 10 billion? All right. Let's do it again. Now again, I'm not doing anything here. I'm just counting, right? But I'm counting extremely inefficiently. And you can imagine that if this was a real program where I was doing real data crunching, it would take even longer because presumably it's not just as simple as adding one, right? How long is it going to take? There we go. I don't know if that count is accurate. Is it? No. It should be what? Was it 10 billion? 10 billion? That sounds greater than 2.147 billion. So let's go ahead and get an accurate count. I can do that by changing this into a long. That's a 64-bit integer. Don't worry about it. This is just for demonstration purposes. When I print it out, though, it's going to have to be an LD, long digit, right? And do it again. How long did that take? Did anybody time that? No. All right, I'll time it. There is a utility called time that will report the user time, the CPU time, and all that stuff. It wasn't that long. It was only, what, maybe 15 seconds or so? Okay. While we're waiting on that to get an accurate version, what if I were to go up a magnitude more? There we go, 15 seconds. Right? Yes, you can use a long int, or a long, you can even go long in some systems. Right? For a 128-bit number, probably not this one. Right? All right, so now I've got an accurate count again, and it took me about 16 seconds. It took me exactly that much this morning when I was doing this. If I went up an order of magnitude more, what was that? Or did I already do that? What was it? There's a million. So if I went up to 10 million, 10 million would be what? 100 trillion? Is that large? Is it? How big is your hard drive? Terabyte? 2 terabytes? Right? That's 2 trillion. This is basically 100 terabytes, right? Yeah, that's a few hard drives, right? But collectively in here, just this room alone probably has that much storage, right? We should be able to process that, no questions asked, right? Now, it might take a pretty good computer or whatever, but let's go ahead and try it. While we're waiting for that to occur, right? Let's do a thought experiment here. I went up an order of magnitude of 10, meaning that this is going to be 100 times slower. Why? Because I've got 10 times 10, within that 10 times 10. So 15 seconds, or it was 16, we'll just round it up to 16 seconds, right? Times 100 is going to be how long? 1600 seconds, convert that to minutes. Probably going to be about 45 minutes, or a half hour, right? If we go up an order of magnitude more of 10, right? We went from, I forget what it was, 10 million to 100 million. 100 times slower. And that becomes not minutes, that becomes hours, right? 44 hours, 2 days basically. Right? This is still not big data, right? This is still small data. This is still, I can store that kind of data on my PC kind of stuff, right? Because the base number here is not anything, right? It's only 100 million, right? That's less than a tenth of a terabyte, right? But we could expect this to go for what, 45 minutes? The takeaway here is when we eventually start looking at efficiency and algorithms and algorithm analysis, is that things like this, a for loop within a for loop, giving a quadratic behavior, right? Squared, right? 10 squared, right? N squared in general, it's not acceptable, right? And we'll see why. But for now, let me kick that back down to just 10, right? And that's very, very manageable, right? How do I kill this? Control C. And it was already took me almost 2 minutes there. It was going to take me another 42 minutes. Okay, so you can have a nested loop within a loop. You can do this as many times as you want, but 3 or more, probably rethink that. Because not only is that 100 times, with 2 loops, it was quadratic. 3 loops, now it's cubic. And an order of magnitude greater 10 is now 1,000 times slower, right? So avoid two if at all possible. 3 and more, there's some rethinking there. Right? It's a particularly bad code smell. So I might have mentioned this before, but things that are smelly, kind of like lint, right? It looks bad. Maybe it is bad. Let's take a closer look. You can also have what are called code smells. Things in the code that the kind of smells. It might be rotten. It might not, because there are things that are supposed to smell bad, right? It was I just saw it the other day. It reminded me of it. It was the durian fruit, is it? Right? It's supposedly delicious. I've never tried it myself, but it stinks. But it's supposed to be good. Lutefisk is another one. I've always wanted to try lutefisk. Does anybody know what that is? It's a fish in lye. All right. I don't know how long it sits there, but it's supposed to really stink, but it's supposed to be very, very good. Right? But anyway, these are code smells. You may want to take another look, because what smells, okay, no, it's supposed to smell like that. We'll leave it alone, but no, that stinks. We need to fix it. In particular, here's some stinky code, right? These definitely have smells, and these are definitely reeky smells that need to be taken care of. Take a look at that piece of code and tell me what's wrong. Yeah, like, which line here? Probably somewhere around here. I do have an I up here. Int I is less than 10. I plus plus. Oops, not that. Ignore that. Cut and pasted in the wrong spot. All right. Let's run this. Perfectly fine. It's a forever loop. Right? That sounds so romantic, right? There's a comment online that's a forever loop, an infinite loop, but a forever loop sounds way more romantic, right? Why is it a forever loop? I like that. That semicolon there, what is it doing? While I is less than 10, do what? Nothing. Right? So, do nothing, do nothing, do nothing, do nothing. Right? That misplaced semicolon there means that we've tied nothing to our while loop, and it gets stuck in an infinite loop. So, do you remember how we can detect lint? How we can sniff out our code to see if these problems exist? Dash what? Wall? The wall flag. The warnings, all of them flag. Right? Oops. Oh, you know what I did? I deleted too much. It was perfectly fine. Now let's go back to the original smelly code here, and guess what? It stinks. Right? And the compiler is now telling, I wish it did say it stinks. There's a code smell right here. But instead it gives us this kind of jargony, the while clause does not guard, meaning that the while clause is tied to nothing here. Right? The statement, but it's misleadingly indented as if it were guarded, if it were applied to the while loop here. Right? So the bad thing is an infinite loop because of a misplaced semicolon. Use a proper linter to define these kinds of things. Right? So software engineering, software development, computer science, whatever you want to call it, it's not like other. First of all, computer science is not a science, right? It's not a natural science. It's a misnomer. Software engineering is not an engineering discipline either, technically, right? Because it's not a natural. It's not a physics-based engineering discipline, right? So what are we, right? We're something completely new, right? At its core, we're math, right? But we're unlike other engineering disciplines, and the example that I usually give is civil engineering, right? If you go over to civil engineering and you go to a bridge builder and they build a bridge and you ask them, you know, what happens if we forget one bolt in the million bolts that we put into that bridge? Is it going to collapse? No, right? There's redundancy in there. One bolt among a million is not going to matter. But one semicolon among 1,000 lines of code, the whole bridge comes down, right? So there is far less tolerance in software development than there is in other disciplines. So keep that in mind. Right? We're different. We're special. All right. Here's another stinky piece of code. Squint really hard. Yeah.
You're not incrementing I.
Not incrementing I. I'm not making any progress towards my terminating condition. In which case, this is going to be a little bit different, but it's still going to be a forever loop, right? An infinite loop, right? But instead of doing nothing, it's going to do something. It's going to print what? 0 until the end of time. We kill these things with Control-C. Eventually they stop. And you're right. The mistake was not remembering to increment this. Right. Good. Did the compiler catch that? Nope, not even with the WAL flag, did it? Why? Infinite loops are perfectly fine. In fact, sometimes intentional infinite loops are required. Right? Think about your operating system right now. Think about the operating system running. It's running in an infinite loop, waiting for me to do stuff like move my mouse around or type on the keyboard. It's sitting in there in an infinite loop, checking, is anything happening? No. Is anything happening? No. Oh, somebody moved the mouse. Now I need to do something and re-render the pixels, right? So sometimes infinite loops are desirable, but not when it's just printing out 0 and doing nothing else. Right? Here's the second to last piece of bad, stinky code. No brackets. Is that okay? Let's find out. There we go. Indent, whatever. So GCC with the wall flag. Right? So this is indeed stinky and it can smell it. Right? It says that the while clause does not guard this statement, but it's indented as if it looks like it should. Indent. Right? It looks like all that stuff belongs in the while loop, but it doesn't. It's just a warning. If you meant to do this, go ahead and do it. But when it runs, same result, 0, 0, 0, 0, 0, 0, 0. Why? Because I forgot my opening and closing curly brackets here. Let me undo. So let's walk through this and why that happens. I is 0. While I is less than 10, do the next thing that you tell me to do. The next thing I tell you to do is only to print it. It never actually makes it down here to line 12 because there are no brackets. If there are no brackets, it only does the next available thing, and that's it. Proper brackets ensure that that entire code block is what gets executed with the while loop here. Don't forget your brackets. Even if you don't need them, even if you are only going to do one thing, right, then still have brackets there because the one time out of 100 that you forget them, you get into a bad habit, and it's just not good. Right? Stay in good, consistent habits and code things like this, always. It's best practice to do so. Okay? All right. Here's our last code smell. And it's a famous one, well, semi-famous one. So does anybody know what the Microsoft Zune was? All right. Did you own one? Anybody? No? Oh, okay, good. So what does it look like? It was an iPod. It was a Microsoft iPod. And it was cheaper, and it had a radio in it. And that's what it had going for it. Right? So they were trying to compete with the iPod, and they never did. Right? It was never that successful. But something mysterious happened to all the Zunes in the world on December 31st, 2008. They froze up for 24 hours. Exactly 24 hours. Right? After that 24 hours was over, they all came back online. 2008 was a leap year. Right? So tell me about December 31st, 2008. What day is that? 365th day? Nope. Leap year is a 366th day. So let's take a look at the code that was in a Zune subsystem somewhere. It's a while loop. So remember, December 31st, 2008 is the 366th day, meaning that it is strictly greater than 365. Our intention is to decrement that back down to January 1st, 2009. Right? We want to take off 366 from the days and add 1 to the year to get to the next day. Is it going to happen? Let's find out. So, days is greater than 365. Is it a leap year? Is 2008 a leap year? Yep. So, this code will get executed. We go inside. If days is strictly greater than 366, is it? No. So we don't do that if statement. We do nothing. This is the else block that we're going to skip because the if was true, right? And so we're going to come back up here to the while loop. And did we change the days? Nope, it's still 366. But 24 hours later, it becomes the 367th day. Let's see what happens then. Greater than 365. It's still a leap year. And guess what? Now this is true. So we decrement this to get down to January 1st. We increment this to get to 2009. And guess what? Our Zunes are back online. Right? So, where's the failure? It should say what here? Or equal to. So days is greater than or equal to. That's the fix. But what really went wrong here? They didn't test anything, right? Or they didn't test enough, right? If you're going to have subsystem code here that relies on the fact that it's a leap year, what should you test? You should test what happens in a leap year. What happens on the first day in a leap year? What happens on the last day of a leap year? What happens on a random day in the middle of a leap year, right? And then take all those tests and do them again for non-leap years, right? Take all those tests and do them for a 5-year period, right? It shouldn't be that hard to automate these tests and test for every single day within a 5-10-year period, right? If you write code to do it, you're automating that. And that's what we were trying to get across to you in your lab this week when we wrote some informal unit testing for this function, is a leap year, right? And then we had you write your own 3 test cases there and build on that. That's automated testing. We'll get more practice with that as we move along, and I'll show you a preview of it next week. Right? But what I wanted to do with our remainder of our time here, and by the way, it doesn't really matter that literally hundreds of people couldn't get their music for a 24-hour period, right? That's not a system critical thing. But again, we are not a discipline where one bolt isn't going to collapse the bridge. We are a discipline where one missing character does kill the entire system. Music, who cares? Right? That's just an inconvenience. But if this were in a system that, say, distributed medication, and we were off by this, right? And somebody gets 10 times the amount of dose that they should, right? They're dead, right? If this were in a system, $100 million system, $160 million, I think it was, a mission to Mars system that failed to convert properly from metric over, or from English systems measurements to metric systems, then the $200 million, $160 million probe crashes directly into the surface of Mars, right? Because nobody bothered to test it. Right? That actually happened, right? Twice. Not the same issue, but both Mars probes died. I think it was 20 years ago or so. Right? So, lack of one single character can kill an entire project, and if that project is like $200 million, right? And there are bugs throughout history like this. There have been bugs that have been in automated trading systems where it was off a little bit, so it triggered a massive sell-off, which of course plummeted the price and plummeted the stock market with it, and it was all due to a computer error, right? They have had bugs in medical systems that have delivered too much shock in a defibrillator or something like that, right? These bugs can be costly in terms of human life or just pure money, right? Don't worry though. The worst that you can do is simply get caught in a loop on the grader, right? And then we just kill it. We kill it after 5 minutes. All right. Any questions so far? All right. Then let's do some exercises. The first one is going to be FizzBuzz. If you've heard of FizzBuzz, then you've heard of that it's a notorious weed out interview question. Right? So if you ever go into a technical interview, I've applied for a data science job and I'm going to be writing Python scripts all day to interface with a bunch of Excel files and automated process and make sure that 3 people are put out of work. Right? They'll ask you, right? We need to know that you actually know Python. So write us FizzBuzz really quick. What is FizzBuzz? It goes back, or it was popularized by a guy called Jeff Atwood. Or at least that's who I'm giving credit to. You will know that person as the creator or the founder of Stack Overflow.com. You search for something, you sometimes get an answer. The top answers are going to be from Stack Overflow. Right? But FizzBuzz, Jeff Atwood, why can't programmers program? There we go. There's a link to this in the recommended reading this week, or maybe it's next week. But what is the actual problem? I'm just going to jump down to it, and then you can read the whole article on your own some other time. But it's write a program that prints out numbers 1 to 100. So in other words, write a simple loop that can go 100 times. But for multiples of 3, in other words, 3, 6, 9, 12, print out the word fizz instead of the number. And for multiples of 5, 10, 15, 20, right? Print out buzz. For numbers that are multiples of both 3 and 5, print out FizzBuzz. So this encapsulates the first 3 weeks of this course. Basic I/O, basic output. Can you output numbers to a line? Check. Can you formulate conditionals, right? If it's divisible by, basic operators and conditionals. If it's divisible by 3, if it's divisible by 5, if it's divisible by both, right? Can you do a basic loop 1 to 100, right? So something that everybody in here is going to be able to do at the end of this week, certainly next week, right? The horror story is that when applicants come in, this is probably hyperbole, but they're able to weed out a significant number of people, right? That claim to have gone through a 4-year degree program, or claim to have had 3 years of Python experience, or 20 years of Java, or something like that. There's horror story after horror story here of people that can't do it. Right? Why? I have no idea. Are they lying? Maybe some of them certainly. Or is there something more fundamental to it? Who knows? These things go back, at least as far as programming, by the way. The original FizzBuzz problem was called the rainfall problem. And the rainfall problem was read in numbers from a user, average them up, and then just keep asking them for numbers. How many inches of rainfall did we have yesterday? How many inches did we have the next day? How many inches did we have the next day? You're summing them all up, and then at the end, to get them to stop, you enter 0 or -1 or something like that. That's your signal to stop asking, and then you sum them all up, and you take the average and you report the average. Same exact thing, right? Basically. Loop, basic conditionals, basic operators, right? And that was a weed out question before FizzBuzz. Right? Can you do the rainfall problem? So it's not like this stuff is anything new. And he was writing about this back in 2007. Right? But to this day, there will be people that can't do it. Don't get incredulous when you take a technical interview eventually and you get something that looks like FizzBuzz. They're not doing it to insult you. They're doing it to get rid of the other 199 people that can't do it. Right? Yeah.
I guess this is a question about technical interviews, but are they going to have you do it right there in front of them?
That depends on the company, right? This is a long time ago, but I interviewed at Epic, which is a medical software company in Wisconsin, and it was an entire day interview. The first half of the day was, well, there was an extended math test written, then there was a timed math test and written. And then after that, there was this really long test of here's a fake language. It was actually not a fake language. It was just a domain-specific language. But here are the basic syntax of it. If you know another language or 2 languages or 3 languages, us giving you the syntax for it, you should be able to do this programming problem. And that took half the day. And it was all written on a piece of paper. I'm sure that it's different now. Google interview questions used to be more brain teasers or whiteboard your solution. I'm sure that they've modernized that now. Like when I did that 10 years ago, the weed out interview was all on a Google Doc, so it was not a development environment. But I had to write code, and they had to sit there and observe me writing code. Then when you actually did the on-site interview, it was all whiteboard. So I'm sure that it's been updated now. That's 10 years ago, so don't take that as fact. Google recent interview experience company X, right? And people will post about it. A resource that used to be a good resource was Glassdoor, and those were used to be unbiased opinions of companies. Like somebody that worked for a company, they could review that company of how it was to be a worker there, including salary ranges and stuff like that. Like, this is a terrible company to work for, don't come, or this is a great company to work for, do come. But it suffered the same stuff that you get big enough, then you start to get the financial pressure from the other side. So I don't know if it's that good of a resource anymore. If anybody knows an alternative to Glassdoor, post it on Piazza. Right. Yep. Okay. So let's prove that we're worthy of this interview. Let's write FizzBuzz. So the first thing I want to do is create that loop, right? Do we want a for loop? Or do we want a while loop? Which one is more? We could do either one. It doesn't matter. But which one is more natural? For int I starting where? We could start at 0, but what was the assignment? To start at 1. All right. So I'm just going to start at 1. You don't always have to start at 0. Right? You could start at 42 if you wanted to. Right? You can start wherever you want. But FizzBuzz is starting at 1. I is less than 100. I plus plus. Yeah, are we going to end up printing 100 there? Nope. We want less than or equal to. Right? Okay. Now, if that was it, I'll just print out the number, %I, or %D and the line, I. There we go. And we're done, right? That prints numbers 1 to 100. But if it's a multiple of 3, print fizz instead of the number. So that's where conditionals come in. How do I determine if something is divisible by 3? If I is divisible by 3, then print fizz instead. But sometimes it helps to write pseudocode like this, fake code, right? Especially if you need to outline a complex algorithm. You would write it down in plain English and then go back in and fill in the blanks, right? I is divisible by 3 is certainly not C code. But we can rewrite it as I, if we were to divide by 3, integer division by 3, and it were divisible by 3, what should the remainder be? 0. Print fizz instead is going to be printf fizz end line. And the key word there, instead, what should I do with this other print statement? Should I do another if? Nope. It's an if-else. You do one thing or the other, not both and not neither. Right. All right, that takes care of the that one. Let's iteratively test this, right? Oops, what did I do instead? There we go. Iteratively test this. A dot out. Right. There we go. 3, 6, 9, 12. Looks like fizz works. Great. Continue. Well, I need to take and check if it's divisible by 5, right? So if it's divisible by 5, then I'll print out buzz instead. Right. Again, should these be mutually exclusive, or should I allow both of these to happen in some cases? The way that I want to write this is to be mutually exclusive. Okay. If you search around for FizzBuzz solutions, you'll get a lot of joke solutions or a lot of solutions that try to do this in a minimum number of lines and do tricks so that you can print fizz and then have another condition to print buzz, without this if-else-if structure. I'm just doing a straightforward one. And then you'll get joke things like, enterprise level fizz buzz. Right. It's all just a joke. It's thousands and thousands of lines of code and hundreds of different source files, all just to print out the FizzBuzz problem, right? It shows how enterprise software can become bloatware, right? Overloaded software. We're just trying to print FizzBuzz here, right? You need like 10 or 12 lines of code. You don't need hundreds and hundreds of files of different things, right? All right, so if it's 5, buzz. Does that take care of all of them? Nope, the last one would be if I mod 3 has a remainder of 0, it's divisible by 3, and I mod 5 is divisible by, or it has a remainder of 0, and so it's divisible by that. Right? Print f is buzz. Probably also fail the interview by misspelling fizz or buzz. Yep. So, how do we, as they say online, that's and is not a keyword in C. Right. It is in, say, Python, but it would be lowercase. It is in SQL, and then it's case insensitive. Here, I use ampersand, ampersand. Yeah. Oh, thank you. So going back to your question on interview questions, right? Are they going to ding you if you make a syntax error when you have to write on a damn whiteboard? Hopefully not, right? That's why, again, more details later, but your exams are all executable exams. It's a open book, open note required computer exam because we will simply be giving you exercises like this. You will write them out and type them out as solutions. You will submit them to the hand-in, and you will use the grader to grade yourself, right? And then I did make a syntax error. Fix it, hand it in as many times as you want until the end of the exam. Right? Otherwise, it's not 1980 anymore. Nobody gives you blue books and has you write code in your blue book. Question over there? Good question, to be determined. All right, let's see if this works. It's not going to, but why? Fizz, buzz, 5. 6 is fizz, okay. I'm feeling pretty positive about this. Until we get to what? 15. 15 is divisible by 3 and 5, right? 15, 30, 45, 60. What's my mistake? This should be at the top. Good. Why? Order matters. The first one that gets evaluated to true is the one that gets executed, and no others. Mutual exclusivity. Right? One of these things will happen. Fizz, buzz, or the number. Right? And consequently, order matters. The most general thing, or the most specific thing comes first, then the most general is last. The most general is that it's not divisible by any of those things, and we just simply print the number. So this thing needs to be hoisted up to the top. There we go. Else. Yeah. And get rid of it down here. There. Is there an improvement here too? If it's something is divisible by 3 and it's divisible by 5, what's it divisible by? 15. That's an unnecessary optimization, but it's nice. Now we're getting FizzBuzz at 45, 30, and 15. I'm confident. Ship it. All right, we have enough time to get started on another one. This is more mathy. Write a program to compute the sum of a partial harmonic series. What is a harmonic series? It's, as I've written it here, it's equal to, there we go. Frac is fraction, not the, anybody who ever watched BSG? Battlestar Galactica? No, okay, before your time maybe. Right. Not even the reboot? All right. It's 1 over 1 plus 1/2 plus 1/3 plus 1/4 plus ... plus, and then the last one that you compute is 1 over n. All right? That's what the series is. Now, normally this n would be infinite, so it'd go off to infinity that, as a real series instead of just a summation. But we can't do that in a computer. We would end up going into an infinite loop. Would we ever be done? No. So we have to have a cutoff point. We will compute the harmonic series out to a certain point, n. Right? So help me out. What kind of a loop do we want now? This is why we have for loops. It's just inspired by math. For I being 1, 2, 3, 4, 5, all the way up to n, right? We have these terms here. So, for int I starting at 0, I is less than or equal to n, I plus plus. Exactly the same thing, same loop as before. I'm going to keep n small here, 4. So we're only going to do 1 over 1, 1 over 2, 1 over 3, 1 over 4. These first 4 terms right here. Okay? Pull out your calculators and tell me what it should be. Double expected value is equal to... All right, fine. I'll pull out my calculator. 1 plus 1/2 plus 1/3 plus 1/4 is that number right there. Okay. The expected value is this number. I'm gonna cut that down. Right. Okay. What's the actual value? Well, that's what we have to compute. Okay. But at the end of the day, I'm going to ask the question. Are the expected value equal to %f and actual value equal to %f equal? Or the same? End the line. Print out expected value and actual value. There we go. All right. We now actually need to compute it to find out. Do we get the answer that we expect? I expect that answer because I did the work manually over here in Wolfram Alpha, or you pulled out your calculator and you calculated it. We formulated a test case, an input and a known correct output. We're going to then get the actual output to our code and compare those. If it's equal, then the answer is going to be yes. Right? Otherwise, the answer will be no. Question mark on both of those. Right? This loop should be pretty simple, though. Right? What should I be doing? I divided by 1 divided by n, right? I need to add that to my running total. The actual value is equal to the actual value, whatever we had before, plus 1 over n. Right? So question mark, where should I start? Or should I leave it like that? Uninitialized values have, who knows, right? Throw the dice. Otherwise, exactly. I should start it at 0. 0 plus 1 is 1. Garbage plus 1 is garbage. So, let's test it. You think it's going to work? Never on the first try. The answer is no. 2.08, that's the expected value, 0? Okay. Oh, well, yeah, what's my mistake, first of all? It's always divided by n. Is that what it is? No, it's divided by I. Okay. We can fix that. Now does it work? Oh, that's different. It's 1. Is it equal to 2.08333333? No. What is this thing right here? An integer divided by an integer will always be an integer. The second we get past 1, then we get to 0.5. 0.5 truncated is 0. Everything after that truncated is 0. Make one of them into a double at least. Save on some code by using a compound assignment operator. And you get a better answer. Are they the same? I would say yes. But would my code? If the expected value is equal to the actual value, then I will say yes. Definitively. No longer a question mark here. Yes. Else? Definitively. No longer a question mark here. No. There. I'm glad I had my linter turned on. What did I do? I forgot to type 2 equal signs, right? And the linter told me about that. So, we said yes. What does the program say? No. They look like the same variables, right? Or they look like the same variable values. But when I go out to, say, 20 decimal places of accuracy, are they the same? Nope. Are they close enough? I'd say so, right? And remember, in engineering, what's better than good? Oh, we don't remember it still? Good enough, right? That's good enough, right? So we should rewrite this to build in some sort of tolerance. Yeah, that's close enough. Right? And that's how we're going to write all of our test cases going forward, right? Dealing with floating point numbers, at least. Right? You do not have to write test cases, formal test cases like this for your Hack 3 this week, right? In fact, we don't even want to see the test cases that you use in your source code. That doesn't belong there. That belongs somewhere else, right? So you put them on a piece of scratch paper, put them in a different file, write formal test cases like this and code them up if you want to, but we don't want to see it. Right? Not yet. After the first exam, we want to start seeing test cases. All right. Have a good weekend.